Our topic in 3.8 is the derivatives of inverse functions. So what do we remember about inverse functions? Two functions are inverses if they undo each other. So one example of a pair of functions that are inverses are y equals x squared and y equals square root of x. So I'm going to explore the relationship between these two functions, and we're going to find some patterns that hold for their derivatives. So if I graph f of x equals x squared, I'm just going to stay here in the first quadrant, so I'm just going to use positive x's and y's for now. If I wanted to, I could take the derivative of f of x. F prime of x would equal 2x. And if I wanted to, I could focus in on one point. If I'm interested at the place where x equals 2, then the y that goes with that is 2 squared, which is 4. So 2 comma 4 is a point on y equals x squared. And if I wanted to find the slope of the tangent line, if I wanted to draw the tangent line to x squared at the point 2 comma 4, I would find my derivative formula, which is 2x, and I would plug in 2 for x, and I'd get that the slope is equal to 4. So notice that's just a coincidence that the y coordinate of the point and the slope happen to be the same, but they are. And here I could draw in the tangent line. It would have a slope of 4 here. Now we already know that the inverse of x squared is square root of x, but we could remember, how did we find that? If we had y equals x squared, we could switch the x and the y, and we could solve for y. So to find y by itself, I'd have to take the square root of both sides. This is how we find the inverse of x squared. The inverse of x squared is square root of x. So I'm going to graph y equals square root of x on the same picture I already have. So that's the one we did in our warm-up just today. If I want to find the derivative, to find the derivative of square root of x, I would think of that as x to the 1/2 power. I'd use the power rule, so the 1/2 would come to the front, and my new exponent would be negative 1/2. So f inverse is x to the 1/2. The derivative of f inverse is 1/2 x to the negative 1/2. Which we could rewrite if you wanted to rewrite that using radicals instead of using exponents that are fractions. You could write 1/2 square root of x. They mean the same thing. Okay, so now that I have my derivative, what if maybe you haven't heard this term before. So we know that functions that are inverses undo each other. If you want to find the inverse of a bunch of ordered pairs, you just take all the x's and y's and you switch them. So if a function f, for example, has the point 2 comma 4 on it, then f inverse has to have 4 comma 2 on it. If the function f had, I don't know, 12 comma 8, f inverse would have to have the point 8 comma 12. Whatever, if an ordered pair a comma b is on a function f, then the point b comma a must be on f inverse. So probably you already knew that, and what maybe you haven't heard before is those 2 points, so in this case 2 comma 4 on f and 4 comma 2 on f inverse, they're called corresponding points. You probably talked about corresponding points on similar triangles or congruent triangles when you studied geometry. So the corresponding point on f inverse, square root of x, would have an x coordinate of 4. It has a y coordinate of 2. And watch what happens if I try to find the slope of f inverse at that corresponding point 4 comma 2. To find f inverse prime of 4, I'm going to take my 1/2 square root of x, plug in 4 for x, and I would find that if I wanted to make the tangent line to f inverse at the point 4 comma 2, the slope there would be 1/4. So that pattern is not a coincidence. The slopes at corresponding points on inverse functions are reciprocals. So that's a big deal. You see that's in your notes. I tried to write slopes are reciprocals as big as possible so that you'll remember that. I want to be very careful to point out that you have experience in the past of finding the slope of a line and then finding the slope of a perpendicular line by finding the opposite reciprocal. Notice there's no oppositing here. And notice these two lines, the two tangent lines, are not perpendicular. So this process has nothing to do with perpendicular lines. But the slopes of inverse functions at corresponding points are reciprocals. Okay, so to fill in, there's a big box at the bottom of near the bottom of that first 3.8 page. So here's what you need to know. If a function f contains the point a comma b and has slope m at that point, so for example we contained 2 comma 4 and had slope 4, then its inverse function, which is going to be called f inverse, that's f with a little -1, looks like an exponent but it's not, contains b comma a and has a slope of 1 over m at that point. So make sure that got written into your notes. This is another way to say the same thing. If I want to take the derivative of f inverse at the x-coordinate of the corresponding point, so in this case at x equals 4, the derivative of the square root of x at x equals 4, that's equal to the reciprocal of, there we go. So the reciprocal of means 1 over the derivative of regular f evaluated at the x-coordinate of the corresponding point on f. So if you wanted to memorize that, that's fine. I have in my life found this statement helpful and I have used it to answer questions. I'm going to show you what I do when I have a question like this to answer. Okay, so if you look at the very bottom of your page, this is how this kind of question usually shows up on the AP test. If I know f is a differentiable function and I've been given a couple of values of f, I know f of 3 is 15, f of 6 is 3. I don't need all that information. They're just putting some extra things in there because part of my job is to be able to ignore extraneous information. I know the slope of f at a couple of different points. And I have a question here. The function g is differentiable, and g of x is f inverse. So that means g and f are inverses. G and f undo each other. Can I find g prime of 3? So g prime of 3 is going to be the slope of the g function when x equals 3. And all the information I have so far, all those ordered pairs that I've been given, they're all about the f function and the f prime function. So I'm going to use this fact that g and f are inverses, and then what I've just learned about the relationships of the slopes of g and f to find g prime of 3. So when I have a question like this to answer, I make 2 separate little t-charts, well, a 3-part t-chart, for the 2 different functions involved. The 2 functions in this problem are f, the function I know a lot of things about, and g, which is the inverse of f. And then the first number I fill into this t-chart, I've been asked to find g prime of 3. That's like them asking me to find the slope of the g function when x equals 3. So notice the very first thing I did was to fill in that x equals 3. On the g function, I'm interested in the point on the g function where x is 3. And then remember what I know. If 2 functions are inverses, if one of the functions contains 3 comma something, the other function must have contained something comma 3. So I'm going to look back through the list of ordered pairs on the f function that I know, and I'm looking for one that has a y coordinate, an output of 3. Once I find that, I can tell that it's when x is 6 on the f function that the y is 3, so I'm going to fill in the 6 there. But now if 6 comma 3 is on the f function, then 3 comma 6 must be on the y function, on the g function, the f inverse function. Okay, so one more step. I know these two slopes, the two missing places in my two tables, they have to be reciprocals. So start by finding the slope of f when x equals 3. Another name for that is f prime. Ooh, I just misspoke that. Let me try one more time. I want to find the slope of f when x equals 6. Another name for that is f prime of 6. So, fortunately, that's one of the things I know. I can read up here that f prime of 6 is -2, so I'll fill in -2. That means the slope of g at the corresponding point must be the reciprocal of -2. That's how I get my final answer of -1/2.